Yeah, now in the next chapter, 5.3, we want to change the process a little bit. We have still 3 PT1s here, but now look what happens. Here, one PT1 is replaced with an integrator. This seems not to be a big change, but really this is a big change. Some things dramatically have to be changed. And furthermore, there is a second change. So here we have 2 changes in the 4th project. This is project number 4. The sensor also will have a gain. Here you see this block 5 sensor gain is 1.25. So I hope this the consequences, the effects of both changes should not mix up in our discussion. There will be a mix, of course, but I hopefully show you that the mix can be separated, that we can see this change comes from the integrator and that change comes from the not one gain of the sensor. But what is an integrating process? Some examples I think should be listed. Let's note this a little bit. So this is chapter 5.3, processes with iPart integrators. Do we have these type of processes? Examples, of course, very often. We will have this. One we have learned, level control. We have a tank level control system. In chapter 2, which we have analyzed, the level of a tank depends on the input and output flow, and the level directly can be calculated from the integrating of input minus output flow. So we have an integration in the process. The same is with position control system. In a position control system, we have a motor, say a motor with a speed motor, and this motor is connected, let's assume, with a belt to a second axis, and then here you can fix something on this belt, and then this movement x is integrating of n dt. N is speed of the motor. Very simple physical relation. The position of the position of the belt is a direct integration of the speed of the motor. So this is a typical integrating process, and in flying objects we have seen in other videos of my lecture that flying objects have 2 integrators in the process, depending, if you have a driving force, the force is integrated 2 times to get the position of a flying object. So we will very often find processes with integrator, so we have to check are there some differences. Here, example with 3 PT1s plus integrator plus sensor. Gain if the sensor is not 1. See workbook page. What do we have here? No, wrong page. Workbook page 42, where you can see the parameters. Okay. Yeah, I call this new project project number 4. And the list of differences I should put into a table. 4 PT1, 3 PT1 plus I. That is project 3. This is project 4. The first difference is the reference and disturbance behavior have same control error, or similar control error, we can say. Control error in ref plus disturbance case are similar. That means if I have no integrator in my controller, reference and disturbance responses have control errors. If my controller has an integrator, then control error in reference and disturbance case have no error, 0. So the behavior is simple. If I want to have 0 control error, take an I and be happy. We will see in the 3PT1 process there is a difference. Difference. This is the first point we have to discuss. Difference in control errors of reference and disturbance responses. Then, second difference between product 3 and 4 is Tn with pole compensation is good, and here Tn with pole compensation is not only bad, but dramatically leads to an unstable loop. It's bad because we have then an unstable loop. What is good in this case is absolutely forbidden in this case. So we have to be careful. Check, is there an integrator or not? Yeah. And the third difference is sensor gain is 1 and sensor gain is 1.25. What does that mean for my final value? Ideal final value is 1, and here ideal final value in the unit reference step, ideal final value is 0.8. So let's discuss these 3 points separately in subchapters. 5.3.1, some words to control error, and I get the control error with DC analysis. DC analysis of system. So first you have to learn how to analyze a system in a DC case, and we use this DC analysis to check the control error here of the project number 4 in different cases if the reference input is not 0 and the disturbance inputs are not 0. So let's start with a signal block diagram. This is my controller, still unknown, could have different types. Then we have 3 PT1s. Okay. The values comes later. Then we have possible disturbance here. I call this Z1. And then we have our integrator. And then we have a possible disturbance Z2. And you will see that at the output of the result of this discussion, there will be a big difference between the position of the disturbance. Okay, let's wait for this discussion. Then we have a negative feedback. And this is the reference input W, Z1 and Z2, and the output X, and here the control difference XD. And here's a sensor with the sensor gain 1.25. Okay, I fill the parameters of these blocks without recording. Now, what is DC analysis? Very simple. Analysis. Very simple. We only discuss behavior at a special frequency point P is 0. In this case, we have a controller gain, which can be written or called FC of 0. Then we can say, okay, all P blocks, PDT1 block, or we have other PT1s, no? PT1, PT2 blocks, proportional blocks. They have the gain, the constant frequency independent gain K. Then we have integrating blocks, IT1, PI, DT1. In DC, they have a gain, and this gain can be calculated to infinity. The gain is infinity. If we have this type of block and we have steady state situation, then we can say, okay, normally we expect a constant output, steady state. That means if we have here a constant value with gain infinity, means the input must be 0. And then we have the D, DT1 and DT2 blocks. There is a DC gain, which is 0. I have mentioned this earlier. And we can say, okay, in steady state situation, we have maybe a constant input. We discuss constant values, then the output is 0. And here we can say, okay, if we have a P or a PD or PT1 or PT2 block with gain K, then constant value input A is the output A times K. Or if we have a constant output B, we know input is B divided by K. Now that are the informations, all valid in steady state case. All values constant. In this situation, now we can analyze the system. We only look for the K values here. K is 1, 1, 1.6. The time constant doesn't play any role because we discuss all things only in the DC case, in the steady state case. Let's start with, if we want to discuss 3 situations. We have 3 inputs, and to separate each input and with its effects on all signals, we discuss 3 cases. I have 3 colors, red, green, blue, and I make in the first case this to 1 and this goes to 0. Second case this 0, this 1, this 0, and third case this 0, this 0, this 1. So I just check what happens if one of the 3 inputs is 1 and the other both are 0. Let's start with the red case. If we have a unit step, a unit constant input value 1 and Z1 is 0 and Z2 is 0, what are with the output, the control difference, or all other values? Now I can just with this information calculate through all other lines. Of course, if this is a 1, we don't know X. So we cannot calculate XD, so we don't know the output of the controller. We don't know all these signals, so we have to have a starting point, and one starting point is very simple. In DC case, if there is an integrating block, then set the input to 0. If this is 0 and this input is 0, of course we know this is 0, then relating to a proportional block, if the output is 0, the input must be 0, this must be 0, this must be 0. And what is with the controller? Note that FC could be a P controller, a PI controller, a PDT1 controller, or a PIDT1 controller. That are the 4 classical types of controller. All other block types have no influence, no meaning, cannot be used, are not common for a controller. Now, these are the 4 typical controllers we have learned in our previous lecture. What happens if the output of the controller is 0, independent of the type, the input is also 0. In red. Input is 0. Then we know if the control difference is 0, the output of the sensor is also 0. And that means the input of the controller is, if the output is 1, is 1. If this is 1, the input is 1 divided by k, 1 divided by 1.25 is 0.8. So we know the output of the control loop is, if the input is a unit step function, the final value of the output is 0.8, independent of the type of the controller. Responsible for this 0.8 is the controller gain of the sensor. Of course, we have to know the sensor gain because this is a maybe electrical value, a 1 volt signal, and only the sensor knows what this 1 volt value is caused by which physical value. Normally, we like sensors which have here a constant factor which is 1 or 10 or 0.1, so that we can by head convert the voltage of the output of the sensor into the physical values, say degrees of centigrade or position values in meter or so. But sometimes this is not true, and of course then we have factor which is not 1 or 10 or 0.1 between measured value and physical value. Okay, that's the first important thing. In other discussions, we can say, okay, independent of the controller, we have always a 0 control error caused by this integrator. This 0 goes backwards up to this point. So we can say, to have control error in the reference case, a P controller or a PDT1 is okay, and both have 0 control error, so we don't need an integrator in the controller, because the integrator in the controller cannot improve the situation. It can only have disadvantage, because the integrator in the controller has negative phase, and negative phase makes a loop slow. So if you want to have a fast loop with 0 control error, take P or PDT1. The best choice is PDT1. Red case, reference behavior. All controllers, all controller types have 0 control error. So consequence is best choice PDT1, avoid PI, pi dt1. So if you have only a good reference behavior, please don't use pi or pi dt1 because these are slower. This is the best case. Yeah. So in that case, very clear. If there is a process with integrating element in its behavior, then just take a P or better a PDT1 controller and be happy with this. But sometimes you have to respond on a disturbance. So in the next case, say green, we set this reference input to 0, but now the disturbance C1 to 1 and leave disturbance C2 at 0. So now here a unit step response comes and we want to calculate the final value of the unit step response on C1. The disturbance step response as final value. What happens if there is a 1? Unchanged is this 0 because this is a fundamental physical law that if the output of an integrating block is constant, the input must be 0. But if there is a 1, there is a 0, we know here we have a -1, a green -1. That means here we have divided by 1.6, a green minus 1.6 divided by a green -1 divided by 1.6, -1 divided by 1.6, and this, caused by the gains of these controllers, goes down to the output of the controller. The output of the controller is -1 divided by 1.6, -1 divided by 1.6, and values, this is 0.625. Okay. And now, what happens with the controller? Now the input of the control difference of the controller depends on the gain of this type of controller. So I write down here the input xt is negative 0.625 divided by the still unknown controller gain at 0. That means, okay, the output, if this there is a 0, this is minus sign, the sensor output now is, here's a good place, plus 0.625 divided by the controller gain at DC case. And finally, we have an output here of the controller loop. The control loop is 0.625 divided by controller gain at 0 divided by our sensor gain 1.25. Okay. What do we want to have here? We want to have, of course, a 0. 0 means I can only get a 0 here if the controller gain is very large, going to infinity. Control error is 0 only if the controller has a very large, possibly infinitely large gain. So we can say, conclude, if there is a disturbance in front of my integrator here, then this integrator is not a help. So this can only compensate it to 0 if the controller has an integrator. So for this disturbance, for the compensation of this disturbance, we need a PI or a PIDT1. We can say green case to compensate Z1, we need FC of infinity fc of 0, sorry, 0 is possibly infinity, that means pi or pi dt1 controller. Otherwise, there will be a control error. That means you are slow. Yeah, so you have very clearly check, is there a disturbance in front of the process? Is this large? Cannot this be neglected? If this cannot be selected, if the user expects that you compensate this disturbance completely, you have to go to an integrator in the controller, independent of the case that then also a reference behavior will be slow, much slower than possible necessary if you have no disturbance. Yeah, so this means the decision which type of controller depends if you have a disturbance case or not. This is different to project 3. There we can say if you want to have zero control error, take an integrator independent of reference or disturbance case. If you can allow a disturbance error, then take a P or PD, then you don't need an integrator. Yeah, that's the difference. To finalize the situation, now I discuss a blue case. The blue case is reference behavior 0, no reference behavior, then Z1 should be 0, and we want to have the situation if Z2 is lying at the disturbance input here. The disturbance at the output of the controller now adds a 1. How large is X? We go with the same ideas back, so the integrator unchanged has a 0 here, and you see the blue case has a 0 here. This gives a 0 here, 0 here, and so on. So we can say the output of the controller is 0, and that means the input of the controller is 0, independent of the type of the controller. The output of the sensor is 0, and that means the input of the sensor, which is the control value in the blue case, is 0. So we have a disturbance here, but reference value 0 and controlled value 0 are identical, so this disturbance is completely compensated with the built-in integrator of the process. So if we want to have zero control error, just a P or a PD is sufficient. You don't need an integrator here or there, which slows down the speed of the closed loop system. Yeah, in green case and blue case, we can say same behavior, same result as red. Design, best choice is PDT1, I not necessary. Okay, to conclude the situation, this case with integrator and the process, if you have disturbance at the output of the process, or if you have reference behavior, then best choice is P or PD. You don't need a PI or PIDT1. If there is a disturbance here, then you have to find a compromise. Either you accept this disturbance error. Yeah, if you have, for example, here 1 volt, you see depending on the controller DC gain of the P or PD, this could be very small and maybe acceptable, or maybe within the limits of the specification. If you can't accept this control error at the output, then you have to go to the slow PI or a little bit faster PIDT1 controller. And then difference number 3 in our list, the comparison between project 3 with 4 PT1s and project 4 with 3 PT1s, I think is also clear, because here you see this sensor with a gain 125 makes at zero control error. So if the sensor output is identical to the reference value, cost in 0.8 at the physical value, we can say. So this sensor gain 1.25 gives an ideal output final value of the controlled variable of 0.8. That is not 20% error as in the case before. This is error 0. So I think the third difference is also cleared. The second difference comes during the design in the next video. So this becomes video number 57.